So if you have not only equality constraints, and we've seen that for equality constraints, for each equality constraint comes a Lagrange multiplier, but with also inequality constraints. So the standard problem is going to be to minimize a function subject to say m inequality constraints and h equality constraints, h I don't know, p. I don't know if there's a. Yeah, we don't really care too much about how many equality constraints, because we know that that case is was treated before. Now, what's an example? Let me just. Well, I gave an example last time where the feasible set was given by two inequality in the plane. So you had, one inequality was restricting the variables to kind of inside of the disk, and another equality was restricting further to inside the disk and inside of this hyperbola, right? So you have two inequality constraints. If you have additional equality constraints, that basically means you're restricting even further, right? So the feasible set can look pretty general. I think I want to venture to say this is kind of a general set in Rn. So X is. Now, the one thing that we're going to be talking about, though, is f, g, and h are going to be smooth functions. So we're not going to. Smooth means it has derivatives of any order you like. Well, at least second order, I think. So we don't have corners. I mean, we may have corners in the feasible set, but that's because there are two different constraints that are meeting at that point. All right, so. So that's the setup, and the idea is the following. So you're trying to find an optimal value, a minimum value for f. Okay, let's assume there is one. Well, if there is one, so assume x star is an optimal solution. Well, if that's the case, there's going to be all the equality constraints are going to be satisfied, and the question is, are there might be some of the inequality constraints that are also satisfied as equality. Then G J of x star is going to be 0 for J in some subset of 1 through m. Possibly empty. Okay, and of course H is going to be, all the equality constraints have to be satisfied, because that's, and I'm sorry, sometimes I forget to put this arrow, sometimes I put when it shouldn't be, but it's really meant to be a vector, and of course H may be a vector, so that's a vector. Here are just, some of the inequality constraints are achieved as equality, which makes them sort of binding constraints. So just think about the linear programming situation. You had, say, you had inequality constraints. Some of those at an optimal vertex were actually achieved as equality. So you had slack variable was 0, right? Made the shadow prices or dual variables to be non-zero. Okay? But this could be this could be empty, or we don't know exactly which of them are binding and which are non-binding. Okay, so this would be binding constraints. But no, regardless of which ones are, if there are any binding constraints among the inequality constraints, then there's going to be Lagrange multipliers associated to those constraints. Okay? So there exists Lagrange multipliers and we use different notation. We use mu j, and of course lambda which is lambda 1, lambda p, whatever. Such that the gradient of f, so that's the optimization, plus summation of mu j, gradient of g j, j belongs to this subset, possibly empty, plus summation of lambda, well, since we don't have a lambda 1, oh yeah, okay, we can do that, summation of lambda L gradient of HL, L from 1 to P, equals 0. Of course, this is all at the vertex, at the optimal, at x equals x star. So remember, why is that? Why was that? Well, if I had these constraints that are equality constraints, Gj and H, whatever, how many equality constraints we have. If we list them, right, then there's exactly those that number of Lagrange multipliers that multiplied with each of this gradient and taking this linear combination, it's the gradient of f. In other words, the gradient of f is in the subspace generated by those gradients, or it's in the tangent space to the feasible set, if we only consider the equality constraints, right? So not all the other ones. But now the question is, if you don't know, since you don't know a priori what this subset might be, and what if it's empty, then here's where this conditions. So in addition, if it's an optimal solution, so if it's a minimum, this happens. But in addition, there is something else that happens. You can actually say that mu, let's see, mu j are positive g of x star is less than or equal to 0 on each component, j belongs to j, and h of x star is 0. Okay. These last two ones are obvious because that's just saying that x star is a feasible solution. Why is this assumption? Why is this mu j positive? Remember, initially when we talked about Lagrange multiplier, we said that lambda for a specific equality constraint, we cannot really say if lambda is positive, then we have a minimum. If lambda is negative, we don't have a minimum. Right? Simply because being an equality constraint, we can always reverse the sign. So, what's the significance of the gradient of this being positive or negative? It means that the gradient of f points in the same direction as the gradient of g, or in the opposite direction. Let's see. If this is positive here, and I just look at gradient of f and this gradient, it means that they point in the opposite direction and the same direction. I think opposite because I put them also, this plus this equals 0. If I were to put gradient of f equals a scalar times gradient of g, then that scalar would be positive if they point in the same direction, right? Basically that means that f and g, so again, the fact that this is positive means that the gradient of f, so mu j is positive, means gradient of f and gradient of j point in opposite direction. I mean, not necessarily 180 degrees, but something like this. If this is the gradient of f, the gradient of g is like this. And it's not, so the angle in between the two is greater than 90 degrees, basically. Okay? Now, let's see, why is that the case? Well, the gradient of g is normal to the equality to the constraint g equal to 0, right? Of course, this is some dj. And the fact that the gradient also points in the direction of increase of g. So it means that g is negative in this region, right? So the feasible set, well, at least if you have one inequality constraint, is, or the gradient of f ought to point inside of the feasible region when you have this kind of inequality constraint. Is that reasonable for a minimum point? Well, if this were a minimum for f, right? But it basically says that it's going to increase as you move inwards, right? The gradient of f cannot point outside of this region. Why? Because then you would go opposite to the gradient and you would decrease. So this would not be a minimum. So again, if you'd like, so this picture corresponds to mu be positive. Whereas if you had a picture like this, of course, this is g less than or equal than 0, right? So this is the feasible region here. And if you go, that's the gradient of g, to have something pointing outside of that, this would correspond to a maximum for f. Or, if it is a maximum, this is how the gradient should point of f. outside of the region, or feasible set. So this corresponds to mu. Of course, we're only talking about a minimization problem. Well, okay, that's a standard. So minimization problem corresponds to the Lagrange multipliers that come from the inequality constraints that are binding to be positive. Okay? So that's why we have this. Okay? Signs of lambda, we don't know, because equality constraints, you can always flip h with negative h. You flip the gradient, you don't have, yeah? But in equality constraints, that's important. Okay? And now the last thing which made, I don't know, made the name of KKT, so that's is in addition to this thing, to add for the complementary indices. So for the, we don't know what J is, right? But for the indexes, so basically for the non-binding constraints, to introduce mu to be 0. So in other words, we're going to have this equality, but some of the mu's are 0. The ones that are strictly positive will be, let's see, I think the ones that are strictly positive, well, some are strictly 0, some are 0, and some are strictly greater than 0. Well, the ones that are strictly greater than 0 will correspond to binding constraints. And of course the other two things here. So let me state. So a necessary condition for x star to be optimal solution to minimization problem subject to g less than or equals than 0, h equals 0 is called KKT condition, which comes from Karush, Kahn, Tucker. So is this the gradient of f plus mu gradient of g plus lambda gradient of h equals 0 at x equals x star. Okay, notice here that mu has how many components? Same as the number of inequality constraints, so that this can make sense. Mu times g is 0. Mu positive, g negative, h equals 0. Let's see, let's look at this and see the dimensions. So here I have n components, right? One for each variable. Yeah. Here I have, again, n components, one for each variable. I have a partial derivative. But I also have m inequality constraints, right? Let's write this in an example to make sure that the dimensions match. But here's this kind of extra thing. So why is this mu times g equals 0? Well, G is m components, right? So basically mu times G equals 0 means mu1 mu m G1 Gm equals 0 means mu1 G1 plus mu m Gm equals 0, right? Now take a look. Mu's are positive, G's are negative. So each of this is negative. So how can a sum of non-positive terms be 0? They have to all be 0. So it means mu j gj equals 0 for j from 1 to m. Okay? So when I write mu g, that really is a row times a column, but in effect, because of this it just says that each component-wise is 0. Now, the fact that component-wise is 0, you have a product of two things equals 0, means that one of them has to be 0. So, if G is 0 on some component, that means you have a binding constraint, then mu can be anything, right? That's the Lagrange multiplier. But if G is not 0, so it's strictly less than 0, you have a non-binding constraint, so then that mu is 0. So that basically says that in effect is mu1 0 0 mu2 0. You have a bunch of 0 mu m. No mu mu consists of, if I'm allowed to write like this, consists of the components of that subset of indices for which there is a binding constraint and the others are 0. Of course, by possibly reshuffling the order. But these are the, and of course this is positive. Okay? Everybody's. So, I have an optimal value. I have an optimal solution. Some of the inequality are binding. There are some Lagrange multipliers for those, right? Well, I fill the rest of the mu component of the mu vector with zeros, and I still have positive greater than or equal to 0. And this gives rise to this condition. Okay? Of course, this condition now is verified, and the rest is just feasible. Okay? Example. Let's take a simple example. So number 311, just since I don't have to write. Just have a product of this has to do with some size of a box. You're trying to use a rope to tie that to tie a box, like you do a gift wrap. So it has three sizes: 1 to x1, x2, x3, which you have to find, and you're trying to maximize V subject to the constraint that you have, which is x1, x2, x3 are all positive, and the sum of the so you have a finite length of rope, okay? And it took me a while to figure out why is 2x1, 2x2, 4x3 until I just took a box and wrapped it. And then you'll see what? You'll see that there is Now I don't know yet again. There are like x1, x2 is the... Yeah, okay. x1, x2 are the top, the size of the top and the bottom. Then you have 2 of each, and then you have 4 lateral ones. So x3 is the height. Okay? Anyway, where a is a constant. So, how many... we don't have an equality constraint. We have a maximization rather than not a minimization problem. And we have 4 inequality constraints, right? So we're going to have 4. Mu is going to be... So the KKT are going to be as follows. First, gradients, right? So the gradient of v with respect to x, so let's partial derivative of v with respect to x1. So it's going to be what? x2, x3, but it's a negative because it's a maximization problem. So I have minus that. Plus mu1, let's see, I think basically use in this order. Mu1, mu2, mu3, right? And mu4. Now these are also greater than or they should be less than or equal than. So it's minus 1 is the first, right? Am I going... Yeah. Well, I'm converting it into a minimization problem. Okay? Plus, now, mu2, the second constraint doesn't involve x1. So there's no mu2. Mu3 doesn't involve, the third constraint doesn't involve x1. So that's it. Plus, and the last one is the right inequality sign. It would be mu4 times 2. Equals 0. Minus x1, x3 plus mu2 times a negative 1 plus mu4 times 2 equals 0. Minus x2, x1, x2 plus mu3 times a negative 1 plus mu4 times 4 equals 0. These are just that gradient relation. Now there's going to be how many? 4 more. Like mu g has to be 0. So there is, let's see, mu 1 times minus x1, if you like, right? Equals 0. Mu 2 minus x2 equals 0. Mu 3 minus x3 equals 0. And mu 4 2x1 plus 2x2 plus 4x3 minus a equals 0. Finally, mu1, mu2, mu3, mu4, positive. Yeah? And all of this listed again. Okay? Now, of course, the book says the following. Says, instead of converting a maximization problem to a minimization problem, why not just think of the same situation, but where we consider the same function and we look at the maximum points. Well, if that's the case, you would have the same things here. Of course, you wouldn't change the negatives to the positive to negatives. You wouldn't change the function like we did here. So this is the same as minimizing minus v. Yeah? But then the mu's would have to be negative, not positive. So in fact, it's just working with minus mu's instead of mu's. Okay? I mean, not a big deal. So that's what it is. What is... At first glance, it seems like we just have lots of equations, lots of unknowns, right? What is the strategy, actually, of solving this thing? The strategy relies here in this mu times g equals 0. Basically says some of the mu's have to be 0, and if not, if a particular mu is not 0, then the inequality has to be an equality. So in other words, if mu1 is not 0, then x1 has to be 0. So it may seem like an inefficient way to solve it, but that's really kind of the only way you can solve this system, is to consider both cases for each of this situation here. Okay? Now, depending on the problem, you may actually figure out ways to simplify that. But let's just imagine for a second that x1 were to be 0. Then you already have this 2 drop, right? What's the most efficient way to solve this? I mean, the book has this one specific way of doing it, but the point is that there is no. There is no recipe of how to, like which way to start looking for solutions. It may be as sort of to have the least sort of involvement in this solution. Would be to say,
what gets rid of the mu1, mu2, mu3 if they solve the first 3 equations in terms of just for mu1, mu2, mu3 and then plug them into the last ones.
Okay, so solve for mu1 here, right?
Right.
And plug it in here.
Exactly.
Yeah. mu2 and mu3. And you still get x1 times this equal to 0, right?
x1, x2, x3, and mu4.
Right. And then he basically says that this expression cannot be 0. Why? Oh, then it finds mu4 in terms of the product x1 times x2 times x3. Then basically it says that x1, x2, and x3 cannot be 0. Which is sort of reasonable because then the volume would be 0. You would have a maximum. So at a maximum, like what is the conditions that happen at a maximum? So basically you get mu1 is 0, mu2, mu3 are all 3 zeros. You can find mu4. You can basically conclude that x1 equals x2 and equals twice x3 or something like that. Okay, so the solution in the end looks x1 and x2 is the same. Oh no. Okay, so I don't want to spend more time here. Just list x1 and x2 equals a over 6 and x3 equals a over 12. Yeah, so that kind of simplifies a lot. If you notice that x1, x2, and x3 cannot be 0, then all mu1, mu2, mu3 are 0. Then you get basically x2 equal to x1, and x3 is half of x1 and x2. And I think plugging back in here, you get the values for the mu's, for the x1, x2, x3. Okay. So it says that basically the box should be, half as tall as thick and wide. Okay. To maximize the volume with a given length. And is that a binding constraint? I think so. I think this has to equal to A. Okay. So all inequalities, well, the third inequality is binding, the other two are not, of course. The fourth inequality, the last inequality. Yeah. So this is binding constraint, the others are not, right? Which makes sense. Still, if you don't have the physical problem to start with, it's kind of hard to say, well, I found now, I solved this KKT system, and I found the x's and I found the corresponding mu's. Mu's are 0, 0, 0, and the last one is a non-zero, whatever. But how do I know this is actually the max or the minimum in this case? Positive. I should have positive. How do I know that this is an optimal solution? And what's worse is if you get a system that has multiple solutions, two or more such sets of such solutions for x and for mu, how do you know which one's a maximum, which one's a minimum? Well, you could say if we don't impose this condition greater than or equal than 0 for mu's, just don't do it, okay? And we find, say, two solutions, one that has positive and one that has negative components. Okay? One of each. And somehow, through another reason, you know that there is a maximum and minimum, then you can match, right? The one that has positive, it's a minimum. The one that has negative values for mu is a maximum. Right? But what if you have one positive and one negative? If you have a solution with mu, that's one positive, one negative. That would probably say you have a saddle point, right? Because, again, remember the mu, the sign of mu basically says I'm either moving, where the gradient of f is moving outside of that feasible region in the direction of in the direction of that particular constraint, or in the opposite direction, right? So you could make that case. But if you have two different solutions that are both positive or both negative, that's when you cannot tell, right? All right. So what do? Well, what you do is you kind of say, in general, this is a tough problem. I mean, it's tough to do a posteriori, how do you say? I mean, it's once you find the critical points. These are critical points, right? How do you decide the nature of those critical points? Well, critical points, sort of the extended function. So let me just say these are critical points for L of x, mu, and lambda, which is f of x plus mu g of x plus lambda h of x, right? Because in the end, the gradient of this with respect to x is 0. The gradient with respect to mu, well, with respect to lambda is 0. And with respect to mu is it 0 or not? The gradient with respect to mu is g of x. So it's not really critical points. Because the g may not be equal to 0 in all components. But the idea is similar with the critical points. Once you find, say, well, let me think. Let me say. Well, I think. Actually, that's true, because mu times g is 0 at a critical point, right? So at a critical point, well, it's tough to say because mu is supposed to be positive here. So it's not. It's sort of on the boundary of this. It's sort of a critical point. It's not really a critical point, but it is the same. To decide whether it's a max or a minimum, you would have to go to a second derivative or do something else to figure that out, right? And you have many more variables that you started with. So it's not practical. So in general, it is very difficult to decide the nature of these KKT solutions unless additional information about F, G, and H is given. Okay. So, what will be one type of information? For instance, again, if you know F goes to infinity, F goes to infinity, as X goes to infinity, and still be inside the feasible set, there is a global minimum, right? And things like that. Or if the G and H form a feasible set that's bounded, okay? Then F has both a max and a minimum. I guess it would be possible to just compute the value of F at those critical points and compare, say which one's bigger and which one's smaller. So it's not that it's impossible, but it's difficult unless you have more information on F, G, and H. Yep.
So in this case, if we let our x's go to infinity, that the equation V does go out to infinity. With the minimum be at 0, x1, x2, x3 equals 0, because then you have no volume.
goes to infinity, but the feasible set here is bounded. So you cannot talk about going to infinity with x.
Because it's bounded.
But because it's bounded, and in fact these are linear constraints, so it's really the feasible set is like for a linear programming problem, right? So it's a bounded symbol x. So you know it has a maximum. You know it has a minimum. Well, if you were to compute the minimum, you would get x1, x2, x3 equal to 0, because that's another solution of this, which I guess shouldn't be ignored, but only because we're trying to maximize with that we ignored it. Yeah. Okay. So the one very important property is convexity. So you will hear about convex optimization and non-convex optimization. Non-convex optimization is so going from one to the other. It's like going from linear to nonlinear. It's a huge kind of jump, and it's it's a very difficult, in general, it's a much more difficult problem than convex optimization. So what is convex optimization? Convex optimization assumes that f, the objective function, is a convex function, and I'll say in a second what it means, as well as g and h are convex functions. Okay, so what is a convex function? In 1D, in one dimensions, n equals 1, so 1 variables, f of x. You've talked about convex or concave up functions. Those are, well, one of the properties that you've seen for concave up or for convex functions in 1D was that the second derivative was positive, right? So f is convex if so that was one property. One property was that the second derivative was positive. But what if there is no second derivative? In other words, what if sometimes it looks like this? Well, this one doesn't even have first derivative at one point, right? So it doesn't have second derivative at that point either. So the question is, what is common between these two? Well, it's kind of that it holds water. I mean, holding water is something, it's not very mathematical. One thing that you can actually say about both situations is that if you take two values of the function at two distinct points, then the graph in between resides underneath the line segment. Okay? So here's the mathematical way of writing it. Basically says that if the function f at an intermediate point is less than, let's say I'm going to use t or lambda, I think t, tf of x plus 1 minus t f of y. So if this is x and this is y, what's an intermediate point? Tx plus 1 minus ty. It's a linear combination of x and y, but with the coefficients that add up to 1. Okay? Imagine like the midpoint. What's the midpoint of these two? Would be 1/2 x plus 1/2 y, right? What's a point that's a third here? A third away from x than y is from x. Then it would be 1/3 x plus 2/3 y, right? So in general, it's that value. So the value of the function at that point, tx plus 1 minus ty. F at that point resides below the value that would be of this point. Okay? I think you do this in calculus 3. You take 2 points in the plane or in space, and then you compute the value, the coordinates of an intermediate point. Basically, the equation of the line between those two, connecting these 2 points. What is that? Well, it's going to be a combination of the coordinates of coordinates of x coordinates. X and y is a bad convention here, but it's basically saying the coordinates, the horizontal coordinates and the vertical coordinates is the same linear combination, right? So what's the height here? Well, this is f of x and this is f of y. So what's the height in between? It's going to be exactly t times f of x plus 1 minus t times f of y. So it's basically comparison. This value is this height compared to this value, which is this height. Okay? So the actual value of the function at an intermediate point is below the kind of the line connecting the two endpoints.
That inequality holds for more than one dimension too?
And yes, in n dimensions it's exactly the same. F is still scalar. So we're talking about a scalar function. So the values of f are numbers. So it's the value of the function at an intermediate. X and y are vectors. And this is a point along the line segment between those two points, x and y. And this is less than or equal than the value of the function, the exact same linear combination with the same coefficients of the values of the function of x and y. If this is true for all x and y. Okay. So, again, I don't know if I did a good job of explaining this inequality, but it really means take any 2 points, even if it's in multiple dimensions, like 2 dimensions. 2 variables. So your graph is 3-dimensional, right? What would it mean? You take 2 points in the domain of the function, you draw the line, and you say, well, is the function, the graph of the function below the line? If this is true for all pairs of points, you have convex function, like that, right? Same is true here. If you have any 2 points here, the graph is below the line segment. Okay? Now, obviously there must be a connection between this and the second derivative of f, if the second derivative exists. So the first thing to say is the following: if f is twice differentiable, well, let me say, so this is same definition for general n. Okay, if f is twice differentiable, on a convex domain, then f is convex if and only if the second derivative, which in the case of several variables it would be the Hessian is semi-positive definite. For all x in the domain. Let's call it K. So what is this? In one dimension, semi-positive definite means it's positive, it's non-negative, right? So that would correspond to what you knew, that we call concave up if the second derivative is positive, right? Or non-negative. But this is true in general, and you have to replace, the second derivative in several variables is no longer a number, but it's the Hessian basically. So this is the Hessian. I called it earlier. Is the Hessian. Of f, right? Okay. So let's say this is one of the statements that is useful, but not very practical. I mean, yes, if you can find the Hessian and you can show that it's semi-positive definite, meaning that at all points in the domain, what you have is the eigenvalues of the Hessian to be non-negative, right? Then that would actually mean that it's a convex function. And I think that would be probably appropriate to do in number 4, which I'm going to assign as a homework. Why is that easy? In number 4. See exercise number 4. If you look at the problem in number 4, it's a quadratic in x. 1, x2, and x3. Right? So being quadratic in x1, x2, x3 means the Hessian is going to be constant. Constant. So it's just going to be a matrix. And that's going to hold, whether that's semi-positive definite or not, it's going to hold for all x's. Not just at a point. Right? But if you look at the problem that we had, in this homework, problem number 1, the Hessian is not going to be constant. It's going to be depending on x. So it's going to be a hard way to actually show. I mean, you can use a computer, I guess, because there are only 2 variables, to, I think, conclude that that's convex as well. But I haven't checked that myself. The other, so this is 1. In fact, and if I have time, I'll give you a proof next time. But at least in 1 dimensions, and actually the proof relies on the 1 dimension case. So in 1 dimensions, what's the fact of the second derivative being positive? What's that saying? That's saying that the first derivative is increasing, right? The fact that the first derivative is increasing, as you go from left to right, it means that the tangent lines are actually, the slope of the tangent lines, which is the value of the derivative, is increasing. So that's why you get this shape, right, of being concave up or convex. Well, of course, there's an additional argument to say, well, why is the fact that the tangent is slope of the tangent is increasing implies that the definition of the convexity, which we said it's the graph is below the line connecting any 2 points on the graph. So that's basically it. But the other very important property of convex functions is the following: if f is convex, actually I think it's if and only if. If f is differentiable, and gradient of f is continuous. Then f is convex if and only if f of y is greater than or equal than f of x plus the gradient of f at x multiplied by y minus x for all x and y in this domain. Now, we're going to be using this inequality quite a lot. So I just want to give you, again, I won't have time to give you a proof of why convexity, the property of being convex, is equivalent to this property. But just in n equals 1, this would translate to say that f of y is greater than f of x plus f prime of x y minus x, right? We'll take a look at the right-hand side of this inequality. What do you see in the right-hand side of this inequality? Say this is x. X is some point here. You see the linearization basically of the function f centered at x, right? Because f prime of x is the slope times y minus x. So f of x plus this is just the linearization or the linear approximation of the is the equation of the tangent line basically at that point. So all this is saying is that the graph of a convex function always lies above all tangent lines. Okay? So it means that the tangent line to any point is always below the graph. Right? Because this would be f of y, and this would be f of x plus f prime of x y minus x. Okay? So that's what property of convex functions is. Main property is that you take a tangent line to the graph at any point, and that separates basically the graph on one side of it. This is true in multiple dimensions as well. In 2 dimensions this is true because it's not a tangent line, but it will be a tangent plane, right? So in any dimension sort of is the tangent space at a point separates basically leaves the graph on one side of the thing. Now, this already gives you an idea why is important then to have G and H, or G, especially G, to be convex. When you have inequality constraints, that basically says a feasible region, which is G, has to be negative, right? That basically will say the following, that any tangent space at any point on the boundary of that feasible set is going to leave the whole feasible set on one side. So the feasible set itself is going to be a convex set that is left sort of is kind of left on one side of every tangent space to that feasible set. Okay? That's one thing, and the other thing is you have f to be convex. So if f happens to be convex as well, then what can you conclude? For instance, if you have a minimum a minimum to a convex function is going to be achieved where? At any critical point. So if it's a critical point, it's automatically a minimum. Why? Well, the easiest is to see here in many dimensions. If it's critical point, this thing is 0. Greater than 0. That's what means the critical point. So f is greater than f at a critical point. So it's not only it's a global minimum. So you have, again, critical point is the only thing you have to find. Can you find multiple critical points? If you do, then this means that the function is sort of constant. Along. I mean, you have multiple critical points. So this is the situation when you have. So for convex functions, it means that critical points are minimum points. Either you have like this, in which case there's a unique critical point and that's a minimum, or it could happen that you have like this, in which case you have, of course, multiple critical points, multiple minimum points, but only one minimum value. Right? And then this is true for basically any dimensions. So what's the? I mean, why do we? It's really restricting the class of minimization problems to very few. I mean, to the case when the function and the constraints are all convex. In that case, we can say we can use these KKT conditions and conclude, by looking at basically at the critical points, or by the KKT points, to say these are minimum. Period. That's it. Because the problem is a convex optimization problem. And I'll leave you with this comment that linear programming problems are sort of a subset of this convex optimization problem. Why? Because in linear programming problems, the objective function and the constraints are all linear, right? And any linear function is automatically convex. Okay, so the set of, basically through this thing we've increased the kind of the range of problems that we can solve from linear programming problems to convex optimization problems. And of course, we left a whole set of problems that we still can barely touch with this KKT, but we have to be in certain specific in fortunate situations when we don't have too many points that we get from the KKT conditions. And so this week we're sort of just kind of restrict to this set. The only really good thing that you can do in this larger set is to do numerical approximations. And that's what we're going to be doing next week. Okay, so first week, second week we enlarge it like this. Third week we're basically going to be saying, well, what else can you do if you don't have convex, or even if you have convex, how do you use, what kind of methods do you use to do that? The last 2 weeks we're going to be going away from this to continuous optimization problems, where we don't have just a finite number of decision variables, but we have infinitely many. Okay? All right. So I'll post the homework. I mean, I'll post it, very shortly. So, but it's going to be due Monday unless you really want it for Friday. So I kind of liked, my intention is to kind of give you a boost on Monday and say, have a homework due by Wednesday, so you just, don't get lazy at the beginning of the week, and then you can get lazy towards the end, but